Welcome back, everyone. Um, this is lecture 11, and we're moving on with chapters in the book. I believe this is chapter 8 in the book. This lecture would be in 3 parts, and we are moving away from England at this point, and we'll talk a little bit about European mathematics of the time, which flourished in the second half of the 17th century, and by far one of the greatest minds of the time was Gottfried Wilhelm Leibniz. He is often described as a genius in many different scholarly subjects, and he left his mark upon each area or subject that he studied. He entered actually University of Leipzig in a very young age of 15, and by age of 20 he had completed his PhD. And while he was in France as a diplomat, he actually discovered the basis or the beginnings of calculus. He was not aware that Newton had done something like this a little bit before him, but nonetheless both men are actually known as the founders of calculus. Anyway, while he was in France, he was actually particularly interested and worked on determining the sums of reciprocal of triangular numbers. So we'll talk a little bit about that, and part 1 would be about this discovery of Leibniz. Okay, before we go on this infinite sums, as I mentioned a minute ago, we'll talk a little bit about triangular numbers and what they are. So the hero of this part certainly is Leibniz. Alright, so triangular numbers, what are they? Triangular numbers are actually numbers that correspond to some triangular array of numbers. Of course, there is a rule to the game. For example, well, the first triangular number would be number 1. The next triangular number would be number 3, as it is required 3 other dots to complete a triangular looking array, and it takes 3 of those. So the next number would be number 6 actually, and the numbers are arranged in this way. Okay, so number 6 is the next triangular number, and then the next triangular number after that would be number 10. So so they look like a triangle, so number 10, and so on. So the first row for each of these will contain a single element, and each subsequent row will contain one more element than the previous one. So here you have number 1, which is considered a triangular number. For the next array of numbers, you have one number here, and the next row will have 2. Here you have 1, you have 2, then the third row will have 3, 1, 2 here, 3 here, the fourth row will have 4, and so on. So basically the kth row will contain k times k plus 1 numbers over 2. So each consecutive row contains one more element. Okay, so what do these triangular numbers have to do with this result that Leibniz proved? Leibniz was actually challenged by Huygens to find the sum of the infinite series. So we are interested in the sum. Well, it's called infinite series because it is an infinite sum. So sum of the infinite series of reciprocals of triangular numbers. So he actually became interested in finding out what this sum will be. 1 over 1. The next triangular number is 3, so we're looking at its reciprocal. The next one is 6, so we're looking at its reciprocal, 1 over 6. Then the next one is 1 over 10. The next triangular number is number 15, and so on. So Leibniz was determined, or challenged rather, to find out whether this summed to a finite number or it was an infinite sum that grew up to infinity, meaning it didn't sum up to a particular finite number. In modern terms, this means he was determined to find out whether this series actually diverged or converged. Converged meaning it sums up to a finite quantity or number. Diverge, it does not. Okay, so after reading about Pascal's triangle, Leibniz actually invented his own version of triangle, and this is called a harmonic triangle. So Leibniz triangle, otherwise sometimes known as the harmonic triangle. Okay, so what Leibniz triangle looked like? Let's see. He used Pascal's triangle to derive his own. And that looked a little different. So let me just write the numbers here and then we'll talk about the differences between the two. So the first row is the number 1 over 1. The second one is 1 over 2 and 1 over 2. Then 1 over 3. In the middle, 1 over 6. And then 1 over 3. Next one would become 1 over 4. 1 over 12. 1 over 12, 1 over 4, then 1 over 5, 1 over 20, 1 over 30, 1 over 20, and then 1 over 5, and so on. So Leibniz triangle also was an infinite one. It can continue to infinity going down. So obviously there are differences between two triangles. So what are some of the key differences between the two triangles? So key differences. Between the two triangles. The two triangles. This is, by the way, a little bit different from the book. Just a little bit different. They don't necessarily talk about the Leibniz triangle there, but the idea of what comes next is basically the same. Okay, so for one thing, the terms of Leibniz triangle are not positive integers, much like Pascal's triangle. They are rather fractions. So the terms of LIB, short for Leibniz, LEB, short for Leibniz triangle, are fractions. So what else one can actually notice here? for example, 1 over 6. 1 over 6 is not the sum of the two elements to the left and to the right on the row above, much like the Pascal's triangle is a little different actually. So 1 over 6 is not obtained by adding 1 over 2 plus 1 over 2. It is rather obtained by adding the number that is diagonally to the left and the number that is immediately next to its left. Well, not adding but subtracting rather. So 1 over 6 is equal to 1 over 2 minus 1 over 3. To the left or to the right, the same idea, 1 over 2 minus 1 over 3. So the rule, I repeat, is subtracting from the number diagonally to the left or to the right, the number that is immediately next to the number in question, to its left or to its right. Okay, so let me just write this down. So the terms, a term is calculated by finding the difference of the term diagonally above it, of the term diagonally above it, to the left again or to the right, to the left, and the term directly to the left, and the term directly to the left. To the left. Okay, so 1 over 6 is half minus 1/3. Same thing for the right. Okay, another difference between this triangle and Pascal's triangle. So, for example, the 7th row here has 7 terms. If you were to continue filling in the terms for each row, you'll notice that the 7th row in Leibniz triangle has 7 elements, whereas the 7th row in Pascal's triangle will have 8 elements or terms. So the 7th row in Leibniz triangle has 7 elements or 7 terms, as opposed to the Pascal's triangle. Unlike Pascal's triangle, whose 7th row has 8 elements. 7th row has 8 elements. Okay. So the reciprocal, here's another difference that it's rather obvious, I think. In Pascal's triangle, the diagonals are all made of 1s, whereas here in Leibniz triangle, the diagonal is made of the reciprocal of the number that indicates the row. For example, this is the 1st row, this is the 2nd row, so the diagonal numbers are both the reciprocals of 2, the reciprocals of 3, reciprocals of 4. This is the 5th row, so these two numbers are the reciprocal of 5, and so on. So the reciprocal of the first term, the reciprocal of the first term in each row in Leibniz triangle will give the corresponding row number. The corresponding row number. unlike unlike Pascal's triangle, while the first term of each row in Pascal's triangle begins with 1 or is 1. Okay, so how does one actually obtain the Leibniz triangle from Pascal's triangle? So here's what you do. In each row, the start, that's, once we know what the differences are between the two, then we can actually start build this Leibniz triangle. So the first number in each row will be the reciprocal of the row number. So if this is the first row, then here you'll have 1 over 1 or just 1. Then to obtain the terms in each row, you are going to divide the initial term by the corresponding Pascal entry. So, for example, in the fourth row, so I'll write the rule and then I'll write the example. So, build Leibniz triangle from Pascal's triangle. So again, the rule is as follows. In each row, the starting term is the reciprocal of the row number, is the reciprocal of the row number. Okay. To obtain the terms, in each row, we divide the initial term by the corresponding Pascal triangle entry, by the corresponding Pascal triangle entry. So, for example, I'll continue here. Here's an example. So, in the fourth row, the initial entry will be 1 over 4, because that's what we're saying in these rules here. So then the entries on the fourth row, how do you obtain this other 2? You will divide 1 over 4 by every entry that it is in Pascal triangle's fourth row. So fourth row here, fourth row of Leibniz triangle starts with 1 over 4. The entries in Pascal's triangle fourth row are what, if you remember or if you can see the notes from last time, are 1, 3, 3, 1. So we are going to divide 1 over 4, the next entries, for the next 2 entries, we are going to divide 1 over 4 by 3, and by 1. So the next entries in fourth row of Leibniz triangle would be 1 over 4 divided by 3, 1 over 4 divided by 3, which are 1 over 12, 1 over 12. Or the fourth row would look like 1 over 4, 1 over 12, 1 over 12, and you still finish with 1 over 4. Okay, so so much for that. Now note the following as well. Each diagonal row after the first, so after, this is the first row. This is not the first row, but sorry. Yeah, each diagonal after the first, so forget about this first diagonal, look at the other diagonals. So each diagonal after the first, if you notice something, is what is called today a telescopic series. This is a term from Calculus 2. As each number actually is formed as the difference of the entry diagonal to the left and the one to the left, or the difference of the entry diagonal to the right and the one to the right. So let me write this. Also note that, and this is actually important for what comes next, I mean this observation. So this is the end of the example. Note that each diagonal, besides the first, each diagonal row, after the first, is what is called today telescopic series. Telescoping series. And for those of you who remembered this from Calculus 2, if not, that's okay. You can always open any Calculus 2 book and see what the telescoping series sums up to. So after the first is a telescoping series actually. Since each term, so I'm talking about these numbers here, about this series. So I'm talking about this one. Okay, since each term in this diagonal series, or diagonal row rather, is formed by, well, is formed as the difference, as I mentioned before, as the difference of the entry diagonal to the left. So 1 over 6 diagonally to the left is half, minus the one that is right next to it to the left, so minus 1/3, is formed as the difference of the entry diagonal of the entry diagonally to the left, and the one that is and the one to the left, and the one to the left, or right, or the right side as well. Meaning diagonally to the right and the one to the right. Okay, see, for example, half is equal to, half is equal to 1 over 1 minus 1 over 2, or 1 minus half. 1 over 6 is equal to half minus 1/3, or 1 over 12 is equal to 1/3 minus 1/4. 1 over 12, 1/3 minus 1/4. 1 over 20, 1 over 20 is equal to 1 over 4, 1 over 4 minus 1 over 5, and so on. Okay, so I'll continue on the next page. I'll bring the triangle up if need be. So this is page 2, and that is part 1. Okay, so what do we have here? Let's see what that sums up to. 1 over 2 plus 1 over 6, and this is a common practice whenever we talk about telescopic series in general. Again, only if you remember from your calculus day. So this is equal to what? This would be equal to instead of 1 over 2, you are going to substitute 1 over 2 with the difference where 1 over 2 came from, and that is 1 over 1 minus 1 over 2. So you substitute 1 over 2 with, again, the difference of the two numbers from the triangle as we talked in the previous page. So 1 over 6 is the same as 1 over 2 minus 1 over 3. Again. And 1 over 12 is the same as 1 over 3 minus 1/4, and so on. Okay, well, if you were to remove the parentheses on this infinite sum, all terms will cancel out with each other. So minus half with half, minus third with 1/3, minus 4 with 1/4, and so on. So you'll be left with what? You'll be left with number 1, and that's what is typical of telescopic series as well. So now, to face the challenge of summing, remember what he wanted to do is find out if the sum of the reciprocal of triangular numbers actually converges or not. So now to face this challenge, he actually used this fact and a clever manipulation of the telescopic series to actually find the sum. So let's begin with that. Finally back to the series of the reciprocals of triangular numbers. Okay, so he didn't know whether that converges or not, but nonetheless, Leibniz called that sum S. So this is S is what we want to actually determine. So S is equal to 1 plus 1 over 3 plus 1 over 6, 1 over 10, 1 over 15, 1 over 20, and so on. Okay. He wanted to determine whether S is finite or not, whether the series converges or not, is the same as saying finite or not, or whether S is actually equal to an actual number, a finite number. In that sense, we mean a finite sum. Okay, so here's what he did. To this equation, he divided both sides, well, not equation, but he divided both sides of this by 2. So we divide first, divide by 2. So dividing by 2, here's what we get. We get S divided by 2 on this side is equal to 1 divided by 2 is half. So the first term, 1, vanishes actually. The second term, 1 over 3 divided by 2 is 1 over 6. The next term would be 1 over 12. the next term would be 1 over 20, the next term would be 1 over 30, the next term would be 1 over 20, and so on. Okay. Okay, well, what is this? This is nothing other than the telescopic series. This right-hand side is telescopic, and it sums up to 1, right? So we have 1 over half times the sum that we want to determine is equal to 1. This is from a step before. So this means that the sum itself is actually equal to 2. And that would actually be the proof. That would be the proof for the sum of infinite series of reciprocal of triangular numbers. Okay, so that leads to the next part, which I'll introduce in a minute. So this would be the end of part 1.